Okay, this is a fun module. This is the module entitled Divergence and Curl Operators. It's fun in the sense that this is it. Once we have div, grad, curl, so we've divided gradient so far, we'll describe divergence and curl now. Those three operations are just emblematic of all of vector calculus. And so you might have seen these a bit before, but now we're going to just live with these operators from now on. And when we see sort of grown-up partial differential equations defined that govern physical systems that you will have to worry about and deal with, they are expressed, if vector calculus is involved, and most of them are, they're expressed using these operators because they're just fancy versions of differentiation. So therefore, in partial differential equations, they're everywhere. And that's how we compactly describe them. Maxwell's equations are just full of gradient, well, in particular, divergence and curl, and then as a result, gradients come into it. Okay? So this is a pretty easy module. We're just kind of defining some things. Actually, executing divergence and curl is pretty much as easy as executing for the gradient. There's just a couple features involved, right? But basically, we've got, as of the end of this module, we have this operation, gradient. We're going to have this operation, which is the divergence, and we're going to have this operation, which is the curl. They're all examples of partial differentiation. They just operate on different kinds of things. They operate in different ways, and they yield different types of results. So the grad operation would be the grad of a scalar function, like electric potential, and the result of it is a vector function, like electric field. Okay? We would have the divergence, and as we're going to see right away, the divergence is going to operate on a vector function. So you have to have a vector function coming in, the divergence of the electric field, for example. And as a result, we're going to get a scalar function. So it takes a vector function down to a scalar function. And the divergence of electric field has to do with the amount of, for example, in total enclosed charge. That's a statement of like Gauss's law. Okay? But now you've taken a vector function, you've got now a scalar function. The curl there's only one thing left, right? Curl is going to operate on a vector function and give us a new vector function. And curl involves cross product, and cross products involve perpendicularity, if you like. That's not a word, but things that are perpendicular to each other. And it's going to have to do with what we call circulation. Okay? And we'll find things like, we could have vector current flowing through a surface, and the curl of the field related to that will give us a magnetic field, which is everywhere perpendicular to flowing current, this kind of thing. Okay? So, really, we're just dealing with these three kinds of differentiation. There's another really important one called the Laplacian, which we'll introduce later. It's also simple. And the Laplacian's kind of curious again. But kind of takes a scalar and keeps a scalar, is what we're going to have. But not for right now. So today is divergence and curl, so these two things. So we're just going to define them, show you a simple example of them, then we're going to move on. Because by themselves, they're simple. We're just going to build them into more complicated things. Okay? So let's go right to the divergence. Okay, so let's just say we have, like we always seem to have, some vector function. Could be electric field everywhere in space, could be the velocity field inside a flowing fluid. Okay, so we've got, and what we're going to do is we're going to say we have, in general, some function, which is its x component, plus some function, in general, a function of x, y, z, which is its y component, and then some function of x, y, z, which is its z component. There's no magic to calling this f. There's no magic to calling these p, q, r. It's just tradition that we do when we introduce these things. Okay? There's no magic to them being capital letters. You don't have to write x, y, z in this. Once we're doing a problem and we know we're in 3D, we understand everything is in principle a function of x, y, z. We're just being very explicit right now at the beginning of everything. Okay? So we're going to have this, and these can be more or less complicated. When we first introduce them, they're going to be very simple. They tend to be polynomials, but there's nothing magic about that either. Okay? So the divergence, we say this, div f, the divergence of f. I just say the divergence of f. When we do del f, and where f's a scalar, we say grad f. That's how often, some people just say the gradient of f. I can just say the divergence of f. You can say div f. There are times in certain books you'll actually see it written like, they'll write this. I've seen this, like div f. I don't know why they do that or where that comes from. And they'll write things like grad, like they'll write it like this. Oh, sorry, they wouldn't write that. They'd write grad f as a scalar. And then they'll write like curl, the word, curl f. I don't know why. I don't know where that really, what the purpose of that is. Maybe it was different typesetting back then where the del operator was hard to type. I don't know. We use this, divergence. So the del operator dot f, a dot product in the vector sense. Okay, so that's defined, right? As okay, so we just write the del operator. Right? That's how it always is. It's how it's been so far. And then think of that as a dot product of this guy. Pi plus qj plus rk, where these are functions of x, y, z, of course. So nothing to it. You just do the dot product. So this becomes del p, sorry, di p by di x. Okay, but now the I vector component that was in the del operator dies against the I vector component that's in the vector function f and saves, so I and I turn to 1, they save p. But I dot j is 0 and I dot k is 0. So the partial of q with respect to x dies. The partial of r with respect to x dies. We're not saying that q doesn't depend on x or that r doesn't depend on x or that the partials are 0. We're saying that those vector components knock them out. So the only thing that survives is this one to this one, this one to this one, this one to this one. Okay? So you just straight up add it, right? Di q, di y, plus di r, di z. Okay? Scalar. In general, this is a function of x, y, and z. Right? So it looks, at very first glance, it looks a teeny bit like the gradient operation, but it's very different. The gradient has I, j, k in there, and the gradient is not the partial of individual components of an f, it's the partial of f itself, because f is just this big scalar function. So where gradient takes scalar gives us vector, the divergence takes a vector and yields a scalar. It's telling us something different. The reason the word divergence suggests what its physical interpretation is, it tells us the extent to which a vector field is diverging away from a point. And just think of the electric field coming out of a charge. Okay? So electric field lines originate on positive charges. So you have a positive charge, empty universe, positive charge. The electric field lines start on the charge and go out. So they're diverging from a point. So if you look at the actual vector field itself describing that electric field, it has divergence because it's diverging. And the amount it's diverging through a physical interpretation called Gauss's law tells us, well, how much charge is in there, right? If we had zero charge inside, zero net charge, could be a positive and negative vector, every time a vector comes out of the space, another one comes in. That's an integral argument. We'll talk about that later. But divergence is telling us about a behavior of the field. And the name is actually mildly helpful. It tells us the extent to which it's diverging or, frankly, converging. So if you had a sink somewhere, actually like a negative charge would be a sink of electric field lines. They come in and die and end on negative charges. So that's what divergence is helpful because it's going to tell us about a property of vector fields that we're going to use in physical laws that we need to deal with. But in terms of mathematical execution, that's the whole show, right? Divergence of f is just pow, write this, where p, q, and r are defined as the components of the original function f. That's all there is to it. Okay, let's talk about the curl. The curl, it's just another operation. Yes, it's a teeny bit more complicated. And there's a couple things I want to mention when we do this. So when we talk about the curl, again, we say we've got f, okay, and we're going to just, I'll just write a little fat, p I plus q j plus r k, all a function of x, y, z. Okay? Yeah. So the curl of f, and that's how you say this, curl of f, okay, is defined as, and I'm using the sort of shorthand for doing the curl, which is the determinant. We'll come back to that in a moment, right? So, and in this, you basically write the unit vectors on top, and then you write the components of the first vector in the cross product, right? And so this is not like del cross f. It is, but we call it curl. Okay? But so we think of this as the first vector, so its components are die by die x, die by die y, die by die z. You don't put the i's and j's and k's in here. They're understood this is just the I component of that operator. And then you say, okay, well, what's the x component of f? Q and, oops, that's why the one. P, Q, R. All terribly general. Whatever the functional form is of the x component of the original vector field goes here, the y component, the z component. This is always die x, die y, die by z. This is always I, j, k, in that order. Okay? And then you use this shorthand for organizing the calculations. You take I, and you multiply it by the determinant of what's left when you cross that row and column. So you go this minus this. So it's die R, die Y minus die Q, die Z. Okay? And then you go on to the next one. And you change the sign every time you go. So this is positive I, that's to be minus J, and then you take the cross of the determinant of what's left here and here. So die R by X, die R, die X minus die P, die Z. Then finally you go plus K, because now you look at this guy, and you look at what's left, and you go here and here, and you go die R, die, oops, easier to do this, die Q, die X minus die P, die Y. Okay. Now that's it. That's it. There's more to it, right? You end up with a vector. There's a bunch of differentials you have to calculate, so there's more calculation involved in doing the actual curl. But formally, that's it. We'll do a bunch of examples of this, and on the exam, there will be one question that says, calculate the gradient of this, calculate the divergence of this, calculate the curl of that. And it's super easy for everybody except for 5% of the people, and that's how it's going to go. A couple things. Number one, I learned a different way to remember the curl in high school. Can I use it? Answer, sure, but stop doing that. Do it this way. This is the more common way. We see it a lot. You'll see more professors do it that way. If you have another way that's correct, sure, but learn the new way. Learn the new way. You don't have to stick with one way. Your brain's big enough. This way. Do this way. Okay? And I've seen every textbook do it that way. That's what you should do. And I'm not saying forget the other one, but your brain is big enough to handle more than one, and you should definitely know this one. Okay. Number two. Note the symmetry going on here, right? So what's happening here is when I do the curl, so this is the x, y, z component of f. Okay. So when I do the curl, the x component of the curl doesn't involve anything to do with the x component of f, right? Nor does it have anything to do with partials with respect to x. So the x component of curl has no die by die x in it. It's all y and z, and only has the z and y components of the original vector, and they're mixed. You take the y derivative of the z component and the z derivative of the y component. That gives you the x component of curl. The y component of curl does not involve partials with y. It's only the partial of the z component with x and the partial of the y component with z. Sorry, x component with z. So it's y term, no y's anywhere. Z term, no z's anywhere. It's just partial y component with x, partial x component with y. So when you write it, not when I'm writing it, I'll often catch mistakes, and I did it right there when I was writing it. If I'm doing the z, I know I can't have z anywhere. If I find myself writing a z in there, I'm like, oh, I made some mistake, right? And it's easy to do. So that's what's happening here. Yeah, that's all we have. So that's how you execute the curl. Okay? And again, we'll do this so many times that you can't help but memorize this. I'm not going to write, in terms of equations you get on the equation sheet, no. I'm not giving you the equation for divergence. I'm not giving you the equation for curl, because you need to know those things. And you can't help but know them after we've been a few weeks of this in class, because we do them constantly. Okay, just a couple identities at the end, and these don't make much sense right now, why we're making this point, and they will come up, but they come up in certain parts of physics too, like Maxwell's equations, where they're capturing a physical property of a system, but right now they're just mathematical identities. So there are two we want to talk about. So the curl of a gradient, and they're both boring, they're both zeros, right? So curl of any gradient. Okay. So that means if I take the curl of the gradient of any potential, any scalar function, it will be zero. Partly, think about this, I sort of said curl has to do with rotation. And I said gradient has to do with being perpendicular to level planes. So you have a scalar function, okay? You have level surfaces and the gradient points straight out. And the curl is kind of asking about how rotational a vector field is. And a gradient is purely non-rotational. So that's why, no matter what you do, if ever you have a vector field that is a gradient of some scalar, its curl must be zero. Okay, I've yabbered a few times about electric field being equal to the gradient of a scalar potential. That means the curl of the electric field must be zero. And it is. The curl of the electric field is always zero as long as we don't have time variation. And that's Maxwell's equation. So the Maxwell's equations, when we have quasi-static behavior, when the electric field changing is not enough to generate a magnetic field, the curl of E is zero. That gives Coulomb's law, but or is equivalent to Coulomb's law. There are times where that will break, and what it actually means is, in those cases, the electric field is no longer equal to the gradient of a scalar. It's something else. It involves a time-varying magnetic field, and that's physics, right? We add more in there. But in statics, electrostatics, where the electric field is always the gradient of some scalar, the curl of E will always be zero. Okay, that's just an example. So a related thing is the divergence of a curl of any curl. So the divergence of any curl operation for any f is always zero. Similar concept. I said divergence is talking about the extent to which fields kind of come into and out of a point, and curl has to do with rotation. They're kind of orthogonal concepts. Okay? This is a very hard or a general sort of statement. Right? So that's the second one. So we have these two. The curl of a gradient is zero, the divergence of a curl is zero. We will pop these out of the background as we need them while we're doing other things. And they generally correspond to certain physical principles that we use when we're doing PDEs, maybe conservation of mass or other things that we're going to have. And some of those involve divergences being zero, that sort of thing, but we'll get to them. Okay, we can prove them. A textbook actually shows this. You could actually formally prove these things, and you can go to the textbook and look through how to do that. For now, though, we will have these in our pocket. Okay, so that's it for. We now know divergence, we know gradient, we know curl, and those are the three classic vector calculus operations. So we're fully in vector calculus now. The next thing to do is to start to integrate things. That's where things start to get complicated.